Let's now consider what happens if a node that is not a leaf becomes too full. So suppose we have the tree we were just working with, and we now add 25 and 26. As you know, we will take the left middle item and send it up the tree. So once it reaches the parent node is now overstuffed. So what I'd like you to do now is try and figure out what you think will happen, just briefly. So here, the 17 is still going to get sent up. And in this case, we end up with a root which has 17. And then the left child will be 15 with its children 14 and 16. And the right child will be 19 and 21. Okay, so it happens pretty much like you'd expect. Now, one last check to see if all this makes sense. Let's think about what happens if the root is too full. So let's suppose we have this little tree here. We add 22 and 23, 21 gets sent up. Now we add 24 and 25. At this point, 23 gets sent up. And now the question is, what do you think will happen? So I'm going to leave this to you to try and figure out. So pause the video and try and write down some answer. So I'll give you a hint. 17 is still going to go up. Okay, so what happens is 17 gets sent up, and it's all by itself as the new root, and it has two children, one, 13, and the other child is 21 and 23. So it happens more or less like you might expect. Now, a really interesting thing I'd like to observe here is that this tree has perfect balance. That is, all of its leaves are the exact same distance from the root, namely 2. So that's very nice. It's a balanced tree. It's bushy. So if we think about this a little more, and we're going to go through a more careful analysis in a bit, we can see that these trees, these splitting trees, that they have perfect balance. If we split the root, then every node gets pushed down exactly one level. You see what happened here? It was all height 1, all the leaves were depth 1, and now they all got pushed down. And that will always happen, because what has occurred is I've taken an item from the old root, pulled it up, and then the two remaining items are left behind. And so we end up now with a tree where every single one of our leaves was pushed down exactly one level. Now, if we split a leaf node, or we split an internal node, the height doesn't change. So in this way, we ensure that our tree has perfect balance. And as a result, we can show that all operations complete in guaranteed log n time. Okay, so before we do the analysis, let's talk a little bit about terminology. And the name I would have used for these trees, I would have called them splitting trees. But I didn't create them, so we're stuck with the real name, which is B tree. Now a B tree, it can have different L values, the limits of how many items can go in each node. A B tree of order L equals 3, like we just used today, those are also called 2, 3, 4 trees, or sometimes 2, 4 trees. Now I know these terms can be a little confusing, and the reason they use this term is it refers to the number of children that a node can have. So a 2, 3, 4 tree has some nodes with only one item, and those can have 2 children. Some nodes that have 2 items, those can have 3 children. Some nodes that have 3 items, those can have 4 children. So it's a little bit taxing to keep track of, but there you have it. There are also B trees of order L equals 2, L equals 10, L equals 55, whatever. You can use any number of L's. And a B tree of order L equals 2, that is also called a 2-3 tree. Now what's funny about the term B tree is nobody knows what it means. There's an old classic quote by Douglas Corner, which is, "The origin of B tree has never been explained by the authors. As we shall see, balanced, broad, or bushy might apply." Others suggest that the B stands for bowing. Because of his contributions, however, it seems appropriate to think of B trees as Bayer trees, after their inventor, Bayer. And just one quick note to round out this terminology, B trees are most popular. The 2 places you see them most commonly are for small l, like L equals 2 or L equals 3. And in that case, it's used as a conceptually simple, balanced search tree. It's a nice, simple way to get a balanced search tree. There are also cases where L is very large, say in the thousands. And that's used, for example, in database applications, and I'm not going to talk about them in this class, but be aware that what we're calling a B tree for small l is the same that you will see if you take a databases course. And here, just to drive home that it's a generic concept, here is a B tree where L is equal to 3, That means the limit of the number of items that can be in a node is 3. So here we got 1, 2, 3. And here is a B tree where the limit is 2. So none of the items have more than 2, or none of the nodes have more than 2 elements. And by the way, just a reminder that L equals 3 trees, those are called 2, 3, 4 trees, also called 2, 4 trees. And for L equals 2, they're called 2, 3 trees. So that's it in terms of the basic functionality of the B tree, how we insert into them. So in the next video, we're going to talk about the analysis and really prove to ourselves that they truly have log n time.